In today's video, we're going to talk about vector-valued functions, and so these are functions of this type: functions that have a domain, which is a subset of the real numbers, and then a codomain that is some subset or the whole set, Rn, where n is just some integer, positive integer. So in at least in the IB course, you mostly learn about functions from the real numbers to the real numbers, or just some subset of the real numbers to the real numbers, and these kind of functions aren't really discussed. So as an example of one of these types of functions, you could look at perhaps this over here, from maybe 0 to 2 pi to R2, and we can define it as y of t is equal to cosine t I hat plus sine of t j hat, where I is a unit vector, which is due east. So that's 1 on the x-axis and 0 on the y-axis, and j is a unit vector that is due north. So that's 1 on the y-axis, 0 on the x-axis, and you can also call these the standard basis of R2. So what does this function do? Well, you can imagine it looks something. Well, we can draw it. It's actually a circle of radius 1. I'll make it a bit bigger. It's a circle of radius 1 about the origin. And it's not obvious what the where the domain is on this circle, because this is just R2. So this is just really the range of the function. The range of the function is a circle. So the domain of the function you can just view as a line. Whoops. So this is one way of viewing it. You go from 0 to 2 pi, and you go from this line to the circle, and that's what this function does. Okay, it maps points on this line to actual vectors which lie on the circumference. Lie on the circle, not on the interior. Another way of viewing what t is, well, t is actually nothing but this angle over here. So that's another way of viewing t. Either way, these are basically just curves, and so we can also just have curves in 3 dimensions. We can parametrize a sphere. So there are a number of different ways of doing that, but instead of parametrizing a sphere, I'll show you a helix. So a helix looks something like this, and well, that's z, that's x, that's y. We can draw that like this. We can say y, is again maybe from, I don't know, this time 0 to maybe 12 pi to R3, and we can call the function. We can do this. So cosine t I plus sine t j, maybe plus t k, where k is just a unit vector over here. So this is k, this is I, this is j. So you would get something like this. At each different level, you'd get a circle. Okay, so it would look like a helix. Okay, so we have sort of, I guess, an intuition of what these functions look like. Now, what does it mean for those functions to be continuous? Well, with normal functions, so f maybe is from AB just to R, let's define continuity on this whole interval, or at a point in this interval. We say f is continuous at a point, let's call it x, in this interval AB where it's defined, if for all real numbers greater than 0, there exists a delta greater than 0 such that if y minus x is less than delta, then the distance between f of y and f of x is less than epsilon. And oh, I just realized something. I've used quantifiers and I've not written the English for them. So this symbol means for all, and this symbol means there exists. Okay, so what's the definition for vector valued function? So let's have a vector valued function from AB to the set of all vectors in Rn. So we say y, well, this is not really a y, gamma, I guess, is continuous at an x in AB if for all epsilon greater than 0 there exists a delta greater than 0 such that if y minus x is less than delta, so the distance away from x is less than delta, then this over here, these distances between these vectors can be made less than epsilon. So although I've used the same symbol for distance, don't be confused, because in R3, for instance, we're really taking a distance between vectors, not points. Although, well, they're really the same thing. But for example, the distance between these two vectors here is literally the length of this line, whereas just working with one-dimensional functions, the distance between this point and this point, is just the distance of this line. So it's still a distance. It's just that we're taking, sort of the distance of a vector, which is the difference of these two vectors. That's another way of interpreting this, and I guess I should put arrows on top of everything that is a vector here. Okay, so let's prove an important theorem about continuity. Well, actually, I won't provide a full proof, but I'll sort of introduce it. In fact, I won't provide a proof at all, because I think that would take too much time. Well, hopefully I'll be able to go over that in the next video. If not, then I'll put the proof as a link in the description box. So there's an important concept that we need to talk about called uniform continuity. So what does this mean? Well, first of all, we need to discuss something called continuity on an interval, and it's pretty straightforward. Let's take a regular function fab to the real numbers, and suppose f is continuous on all points in AB. Then we say f is continuous on the interval AB. Okay, so that's straightforward. Now let's discuss uniform continuity. Let's first just state it. Let's state the entire thing, the definition, and let's do some explaining later. So uniform continuity. F is uniformly, I'm not going to write the whole thing, continuous on AB if for all epsilon greater than 0 there exists a delta greater than 0 such that if x minus y is less than delta xy are in AB, then f of x minus f of y, the distance between f of x and f of y, can be made less than epsilon. And this must apply for any two xy in AB. So this looks awfully similar to the definition of discontinuity. So what's the difference? Well, you can think of this as a sort of global continuity. So what this implies is, if this is an interval AB, then as long as we, let's say, are a distance, as long as we choose 2 points that are a distance less than, let's say, 1/10 apart, we can ensure that the images of those 2 points under the function f are always a distance less than, epsilon apart. Let's say epsilon in this case is 0.001. And it's not just, for a certain point or around a certain point, it's literally any 2 points in this interval. So we can literally choose any 2 points in this interval as long as they are closer than 1/10 apart, their images are guaranteed to be closer than 0.001 apart for any 2 points. So if a function is, just continuous at a point, what's different is you need to be, let's say, a tenth close to that point for the images of that specific point under f and a point that's a tenth close to f to be a certain distance apart. Here, you don't have to only be able to, you need not only specify a point, you can just choose any 2 points that are less than 1/10 apart. Not just, you're not interested in only 1 point. So it's, in a sense, it's like a global sort of continuity. So, whoops. Okay, I think that's enough for one video. In the next video, we will hopefully prove uniform continuity. But if I decide that that may take too long for one video, and it's a bit too involved, then I think I'll put the proof of that on my blog, and I'll put a link in the description. So in the next video, either we'll prove uniform continuity, or we're going to start talking about work done. So, whoops, work done, which is actually a concept in physics, but is explainable, I guess. Whoops, explainable and expressible in math, which is why I'm doing a video on it. Alright, so thanks for watching.